Apollo Houston, I got two messages for you. Moscow is go for docking. Houston is go for docking.
So I think we have taken a great step, that indeed we have opened a new era in the history of man on this, and it will be beneficial.
Come the 70s, and Harry Stephenson is again focused on saving lives. He knew that even with the benefit of ELT beacons, rescuers still had a hard time locating a crash site. In 1971, with the space age in high gear, Harry wrote a groundbreaking technical report detailing the possibility of using satellites for detection and location of ELT signals. His vision included much of what exists today, such as multiple orbit trajectories and unique beacon coding. And look at the artwork on that. And that was before personal computers. These studies inspired others to make the concept a reality. In the case of Canada in 1972, fate gave a not-so-gentle push. Larry Maynard was a flying enthusiast with his own float plane. One evening, while his plane was moored safely at his dock, the 121.5 distress beacon on board activated due to an electrical malfunction. The distress signal was picked up by an overflying aircraft. In the middle of the night, the Canadian Forces helicopter flew in to rescue him from his warm, cozy bed. Although embarrassing at the time, including many apologies to the SAR crew, it became Larry's "guess what happened to me" story over coffee the next day with his technical team. You see, Larry was head of the Space Systems Group at the Communications Research Centre, CRC, in Ottawa. As he recounted the lecture he received from the SAR techs, it occurred to him that he should challenge his group to try to build a space system that would allow satellites to determine the location of distress incidents, shorten the time to get to the rescue, and significantly reduce the cost of searching, particularly in Canada's Arctic region. NASA was also looking into a similar concept as part of their push to develop new space applications.
In 1974, they were looking for a project leader for Sarsat, this little project that seemed to be a gleam in somebody's eye. Sarsat was not in the CRC mainstream. We had to scrape to some extent to have people. Many of the D&D projects were studies, but they really didn't go very far. But this one was a bit different because it had public pressure. Why was it taking so long to find bush pilots in the north and so on? And there were several celebrated cases. One of those included a pilot called Hartwell, and that got national attention.
In November 1972, a medical mercy flight with 4 people on board, flown by Martin Hartwell, went missing in the Northwest Territories. 2 separate searches failed to locate the downed plane, which, unknown to SAR, had strayed hundreds of kilometers off course. His aircraft did carry a 121.5 distress beacon, which, as was typical of the time, Hartwell activated only when he heard an overflying aircraft. By chance, the plane overhead was a military aircraft on an unrelated mission. They picked up the signal. He was rescued 31 days after the crash. He was the only survivor.
And so there was pressure on actually doing something about trying to find people in the north. The whole push of the space program in DOC was that it open up the north, both for communications and remote sensing.
In the U.S., just 1 month earlier, on October 16, 1972, another high-profile tragedy took place when a private aircraft disappeared in Alaska. This aircraft was not equipped with a distress beacon. This search and the Hartwell search in Canada became the catalysts that would soon impact search and rescue right around the world.
2 congressmen in the United States who were flying in a light airplane from Anchorage, and they disappeared en route, and I can't remember the number of thousands of hours that were spent looking for them, but they were never found. And it was a congressman from Alaska, Begich, and Boggs from Louisiana.
Well, I think that provided a lot of impetus because what happened was Congress then passed a law that said you will have ELTs on, you'll have emergency transmitters on airplanes. You will have, no doubt about it. And then the Coast Guard said, well, gee, that sounds like a good idea to us to have them on boats too, so let's put them on boats as well. So that's how the beacons came about. Unfortunately, Congress didn't really say how they were going to detect these beacons. And then that's where NASA came in.
When the ICSAW looked at the situation, they said, here's an obvious case where the problem with the ELT is not so much that they don't have ELTs or that they don't go off. Well, they go off too frequently sometimes. But that there's nobody there to pick them up. The search area of an airplane is fairly limited. So the idea was very simple, that if you could observe this from a satellite, you'd cover thousands and thousands of square miles, maybe a radius of maybe 1,600 nautical miles, as opposed to a tenth or a 20th of that from an airplane. So it was a natural match.
Canada was the first out of the gate. Researchers there were used to figuring out how to make inroads on a shoestring budget. And in a surprising twist, a tape measure, not unlike this one, played a key role in proving that a satellite could really measure up to the job. See if you can figure this one out.
So we wanted to see where the technical challenges were to be able to put a whole system together, not just one piece. So the system included ELTs, it included the spacecraft, it included the ground processing. A lot of research had been done on the US, the transit satellites, for example. I mean, there was a lot of interest around of trying to find pilots who had gone down, and I think DND got permission to release that to us.
So the unknown that CRC needed to solve was uplink Doppler. That is, they already knew that downlink Doppler from transit satellites could be measured. So the question was, could uplink Doppler from a weak ELT signal be detected and measured? To solve this problem, they needed two things: an available LEO satellite and somebody to figure out how to calculate its precise position throughout its orbit. Enter Rich Renner, Mike Stott, and Oscar.
This goes back to Kepler, orbit propagation based on an elliptical model. The problem with the Earth is that it has bumps and valleys and everything. The best answer was to do numerical integration. First of all, you need to know where the satellite is at every time that you take a measurement. So what you have to do is you have to predict its ephemeris, or predict its position at all times. So what you do is you have a set of equations, second-order differential equations, which I had to program on a teletype. My background is mathematics, so I just applied the equations that I knew and coded it. But, you know, when you do any coding, you always have to be very careful and test and test and test. And the Oscar satellites were ideal to be able to try to perform this special test.
And so we arranged to use the Oscar satellites rather than build, a very expensive simulator. It would be a useful and fairly quick way of using the satellite repeater at a frequency, of course, which was somewhat different from ELTs, but not that far away.
Oscar 6, Orbiting Satellite Carrying Amateur Radio 6, was designed to transmit a signal from space that could be used by ham radio operators across the globe. It was built not by a space agency, but privately by volunteers. Fortunately for Alan, one of the builders, Larry Kaiser of AMSAT, actually built a good part of Oscar 6 in his basement in Ottawa. Alan was able to talk to him about his idea. He believed access to the satellite would be extremely beneficial to this project.
CRC, being smart young men that they were, they decided, well, in order to make this happen, all we have to do is take a look at the beacon and just change its frequency. And that's what they did. They changed it from 121.5 up to, I think, 145 megahertz or something like that. And it worked.
So now that Rich Renner and Mike Stott had developed a formula to compute a satellite position in space, the next challenge was to use that satellite to detect a very weak, unstable analog beacon signal and determine its location on Earth.
So given the measurements of frequency and time, I was tasked to find the location of this 121 megahertz beacon via satellite. The problem was that these beacons were very, very weak. They were transmitting at around 250 milliwatts or less. And so what happened when you receive them from the satellite, the signal is so weak that in order to detect it, you had to go right down to the very noise floor. So what that meant was that here we had a stable frequency in a background of noise. So in order to try to find this special frequency, we came up with, at the time, a brand new algorithm which was called a fast Fourier transform. And this allowed us to be able to take the signals that were available from these beacons and digitize them. What we then found out was, with the satellite overhead and passing over the beacon, this particular signal would provide a Doppler shift, whereas the regular noise floor did not have this pattern. So we came up with another special algorithm, or what we called a curve sorter, and what that did was sort out all the data that would follow a specific Doppler curve. We tried every possible Doppler curve, and when we had a match, we extracted the data and then proceeded to locate the particular beacon.
The permission we got was from AMSAT in April, and by the 6th of June 1975, we had the system operating and we could locate reasonably accurately ELTs within 20 miles, let's say, at that stage. So that was in April. Well, it was 5 months later that NASA contacted DOC.
NASA, or our Space Administration back then, knew we could use Doppler technology to locate transmitters on the Earth's surface. So the Coast Guard and the Air Force, they went to NASA and said, can we use satellite technology to detect these beacons? And NASA started looking into it.
And they provided a bit of a briefing on their interest, and we provided a briefing on ours. And they said they'd heard that we were using the Oscar satellite.
The person assigned to oversee exploring the idea of satellite-assisted search and rescue for NASA was Bernie Trudell. He would turn out to be the perfect choice for this mission. He had exactly the right combination of technical expertise, vision, drive, passion, and audacity to move this project forward.
I don't know at what point or how it came about that Bernie got into it, but I know I talked with him at some of the very early stages, and I know he was a mover and pushing the system and pushing it and saying how great it could be and what it could do, and give me a little bit of money to work this thing out. We can make it happen.
We used to call him the proverbial used car salesman, and he was forever going, into the Goddard management and NASA headquarters, trying to sell this program. So he was not only an engineer, but he was a salesman too, an entrepreneur, if you will, and as a result, it was kind of exciting to work with him.
He did a lot of horse trading with the system. One of the stories is that the reason it's called Cospas Sarsat is Bernie wanted something, so it was Cospas Sarsat instead of Sarsat Cospas.
Hundreds of people contributed to the success of the program, but Bernie's impact overall in bringing the program to fruition was so massive that he became known as the father of Cospas Sarsat.
Bernie Trudell was pretty dismissive in the early days of why we would use Oscar satellites. I mean, if we think of NASA, and I came to appreciate this when I spent every month down there, was that they had access to infinite number of resources.
Typical of the time, A satellite assembled by amateurs was not necessarily taken seriously by NASA, especially given the fact that it likely used surplus components donated by space electronics manufacturers, not to mention a 10-foot carpenter's tape measure that served as its antenna. But Bernie quickly came to realize the wisdom and practicality of using this homemade spacecraft to test beacon detection.
So Bernie Trudell, on his side, was assigned as a project leader, and I was assigned a project leader in Canada. So he began to see that what was really important here was that we support each other as we went through this program. By the end of December, Dan Brownell, who was one of the people that was with Bernie, had already run an Oscar experiment. So they didn't want to be left behind on that score.
NASA had all these codes in there. Code 600 was the engineering group there at the time. They did some experiments that were pre-Sarsat. They were on the Oscar satellite to prove the concept of being able to detect and locate beacons.
Bernie and I had worked on putting together what a Sarsat program would look like and approximately what the cost of that would be, and especially if you shared it between the two countries.
So NASA faced a conundrum. Should a new satellite system designed for search and rescue service thousands of beacons already available, but at the same time were not particularly reliable, or build a brand new type of beacon, rendering existing beacons obsolete?
We were, both NASA and ourselves, interested in the whole system. And so we were sharing quite a lot of information on ELTs, on, attitude of pilots towards ELTs, what were the real issues. So there was an interest, I think, in making this as effective as possible for users. I mean, of course, NASA's interest was in the long term, and that was around the 406 megahertz beacon, etc. But as they started to deal with the Coast Guard and the pilots' associations and so on, they realized that there was a big pushback from those groups in going beyond the existing ELTs.
It was decided to keep the focus on using 121.5 beacons for the present time, knowing its limitations.
They did not want to move to 406 in those days, and I think there were good reasons for that. I think the program would have stopped if everybody who was against spending more money and red tape and so on planes. But we all realized very quickly that if you look at the satellite design and you look at the field of view, that you were quite limited in the number of simultaneous alerts that you could actually transmit at 121 and 243. And so there was a lot of interest in designing an ELT that would actually be designed for the satellite system. So that would be short bursts, they would have an identification in them. And that was already being used in weather satellites and other things like that.
CRC had one more hurdle before the satellite-assisted SAR project could move forward. To fund the next phase of this project, they first had to impress the Chief of Air Doctrine and Operations, Canadian General G.A. Mackenzie, and they only had one chance. That would take place right here at Shirley's Bay in September 1976.
Unfortunately, that became, to some extent, an all-or-nothing demonstration. It was an amazing event because CRC had never seen so many DND staff cars arriving at the front gate. They didn't realize that, of course, this demonstration was in a small hut at the back of CRC. So there was only room in the hut for General Mackenzie and one of his aides. And so the others were all crowded around the door. General Mackenzie had arranged to take the simulated ELT away and he had arranged for it to go to a place that only he knew. And he had marked this with a Latin long on the map. And so when the pass happened, which was quite early in the morning, we then decided to lock onto that pass. And thankfully, it really was thankfully, everything worked well. the way the machine worked was it made a guess and then it worked its way in towards the final answer. So General Mackenzie, when he saw the first guess and he looked at his map, I think he felt, well, these guys haven't done it. They're 100 miles out. But we said to him, you know, this will take about a minute. And it worked its way in and it got to within 2.8 miles of where he was. And he just looked at the map and I could see his face change. And he didn't say anything. He just stood up and he walked out of the hut. And on the way out, he was there. He whispered to me, "You've got your money." And that was the end of it.
After General Mackenzie's approval, things moved very fast. Canada and the US formally signed an agreement to put together a document which would lay out the technical understanding of the system.
It was only as we got into that definition that NASA said, oh, by the way, we have an arrangement with CNES, which was the space group in France, to fly a 401 transponder on our weather satellites. And so they said, what we could do is just repeat that pretty well exactly on the Sarsat system. And if the French would pay for it, this would be a very good thing to do. And I think everybody felt this was positive.
France was approached and was very enthusiastic about the idea. Their expertise in satellite-based tracking technology would prove invaluable when the system went digital.
Okay, during the 70s, France developed two satellite programs using Doppler location techniques, the EOL program and the Argos program.
The Argos data collection system was used to connect data on automatic beacons on board anything, on board ships, on board floating buoys, on board balloons, on board anything, anywhere in the world.
These two programs were developed in cooperation with the United States. So when it comes to develop the Cospas Sarsat program, France proposed the use of its technology for the 4C MHz system.
We had a series of different people who talked to at headquarters, but the key man at NASA was Bernard. We set up technical team in Toulouse next to the Argos team, and they started working together with the NASA Goddard team and the Department of Communication of Canada at the time.
So in the Cospas Sarsat system, France's contribution is the receiver processor at 4.6 MHz, which, associated with the Canadian search and rescue repeater, are installed on the NOAA Tyros meteorological satellite to provide for the Sarsat part of the Cospas Sarsat space segment.
The technical challenge of the receiver processor was what we call random access. In other words, the signals are received by the receiver in a random fashion. And in fact, in Sarsat, it is exactly the same system. Instead of working at 401 MHz, it works at 406. I would say the additional challenge in Sarsat was that a fix needs to be obtained right away, which means the priority was to get a fixed geographic position of the beacon.
But those of us that were technical realized that a 406 transponder limited the 406 system quite drastically because it was an onboard processor. So you couldn't change the ELTs after that once the spacecraft was launched. And the ELTs had not been defined and they had not yet got to a point of being approved or anything like that. So there was an interest then in Canada in trying to make sure we had what we call a bent pipe 406 transponder on board as well. So this would just take whatever we received at 406 and transmit that back to the ground station. So actually, I think everybody felt it was a win-win. The French felt it was a win because they wanted to fly this processor, and NASA wanted that to happen. NASA's view was that they wanted to develop technology, and Canada's view was, yes, eventually we'll have to think about 406, and if we do want to do that, well, here's an experimental system we could use.
Having both the 406 bent pipe repeater and onboard processor payloads on Sarsat satellites turned out to have unexpected advantages. These included providing a backup in case one of those systems failed in orbit, thereby extending the operational life of the satellite. Additionally, the repeater offered a visual display of the unexpected RF interference in the band from emitters that were not beacons. Furthermore, it allowed for evaluation of new 406 beacon signal variants to be tested using the satellite repeater in real-world conditions. The reliability and efficiency of both SAR payloads is undeniable. The same fundamental equipment design that was first integrated into Sarsat satellites launched in 1983 are still in service in 2024, and some of those payloads remained operational for over 20 years. It is amazing that we had it right the first time.
The U.S. and Russia, after the Apollo-Soyuz mission, were looking for other ways to cooperate in space. Since this mission was humanitarian, it was search and rescue related, it was easy for the two countries to try to work together.
There was a desire for cooperation on the space application that wouldn't have strategic implications, because that was one of the issues of the time. No technology transfer, no strategic application, implication of a new technology that could be shared. And search and rescue was a good, humanitarian endeavor, politically good to sell. And I think that was the reason why they wanted to do that.
So it was a very significant milestone that they could cooperate and develop standards and operate a system like this for humanitarian reasons.
В 1978 году Советский Союз получил от Соединенных Штатов предложение совместно участвовать в создании международной космической системы для поиска судов и самолетов, терпящих бедствия. Согласно идее, которую уже 2 года тому назад, то есть в 1976 году, разрабатывали американцы, канадцы и французы, в систему должно входить 2 метеорологических спутника. Они оба из Соединенных Штатов.
NASA and their equivalents in the USSR would have regular meetings at the IAF congresses. And the congresses were alternately behind the Iron Curtain for 1 year and in a Western country for the other year. So it gave people the opportunity to talk about really things like interference of satellites. The Molnar series was interfering with Intelsat, those sorts of things, and it gave a forum for that discussion. So there had been some discussion going on between them. NASA, I think, would tell the Russians generally, upcoming programs, because they wanted to coordinate those programs from a frequency point of view. And the Russians would do the same with the Americans. So there was some interest, but it was really quite fascinating because just a telex came out of the blue into Canada, and it was on the 4th of February 1977, and it basically said, we have had a request from the USSR for a briefing on search and rescue, and it will happen in another couple of months, and we expect, in quotes, we expect Canada to provide part of that briefing, and please advise whether this will happen.
That meeting would prove to be quite consequential. By inviting the Soviet Union to participate in this humanitarian effort, this space program could instantly double the number of satellites and reduce average distress alert detection time by half.
То у них было большое время ожидания, порядка 8 часов. Если добавлялась новая подобная система, в данном случае советская, то она также должна была содержать 2 спутника, и в общем системе появлялось уже 4 спутника, и время задержки уменьшалось в 2 раза, то есть становилось уже 4 часа. А время задержки – это основной параметр такой системы, поскольку эффективность ее определяется тем, как быстро сигнал от аварийного буя окажется на приемнике спутника и от него будет передан на Землю.
Equally important, it would provide this fledgling system with an international profile and recognition by United Nations agencies including IMO, ICAO, and ITU in the coming years.
I think at the end of that, I think people felt that there were good principles. I mean, one of the principles was that there would be no technology flowing between the Canada, US, and the USSR, that essentially we would share specifications, but nothing else. And I think that really helped, that guideline really helped establish probably for DND as well, the fact that this could go ahead as a possibility.
One sticking point was the Russians only wanted to use the 406 frequency. They felt that 121.5 was outdated and fairly useless as a distress frequency.
В судах и в авиации. Поэтому, когда начиналась работа по определению состава полезной нагрузки на спутнике Cospas, это советский спутник, то возникли у Советского Союза вопросы о том, нужно ли ставить ретранслятор таких сигналов, которые вообще несут на себе отпечаток прошлого, их нет практически у нас, и они не перспективны из-за точностей определения координат. Но после обсуждения с делегациями США, Франции и Канады все-таки было решено поставить такие ретрансляторы, так как после запуска первого же спутника придется работать с большим количеством, около 250 тысяч на тот момент, радиобуев на частоте 125 МГц. А в то время перспективных буев аварийных, работающих на частоте 406 МГц, практически еще не было.
The French officially signed up as part of Sarsat in August 1979. The Russians officially signed up to be part of what would then be known as Cospas Sarsat in November 1979 at a meeting in Leningrad. And Cospas Sarsat was born.
Using the Oscar 6 satellite did accelerate the program. Many satellite programs have to go through different phases. You know, there's a study phase, a technology development phase, a proof of concept phase, often a beta phase or a phase, a pre-operational phase, and then an operational phase. By using the Oscar 6 satellite and convincing people that the technology was there, it accelerated past the technology development phase and past the proof of concept phase right into essentially a pre-operational phase. The time saved was probably several years, and to be able to estimate that, you can look at other systems that have gone into place. For example, the MSAT system. MSAT was being talked about at the same stage as Sarsat in the 70s, but by the time MSAT went through proof of concept and became an operational system, it was well into 1995.
In 1979, the International Telecommunication Union, ITU, allocated the 406 to 406.1 MHz frequency band specifically for worldwide distress beacon use at the request of Cospas Sarsat. Simultaneously, the ITU allocated a 1544.5 MHz satellite downlink frequency, also referred to as L-band, to relay distress signals back to Earth. This means that these frequencies are protected from outside interference. These bands are not owned by Cospas Sarsat. Other satellite operators coordinating with Cospas Sarsat could potentially use the same frequencies for their own distress and safety services. By the end of the decade, most of the technical hurdles and political tensions were overcome, and the parties were in place to change the face of search and rescue forever. We are go for launch!
Is that a cumulative or is that